Okay, so today is the last lecture before the course conference. The prize for the conference has arrived. I have it in my office. All right. So I want to finish up the random matrix theory, and then I want to try to do some of the differential privacy, because I think that's pretty interesting. How many of you have come across differential privacy? Okay, maybe about 4 or 5 of you. Okay. So for you guys, it might be a little bit redundant, but for the rest of you, it's a pretty hot area. It's quite interesting. And I think we'll have time to do at least some of it today. So let's finish the random matrix. If I'm on page 4, actually, there's a little bit on page 3 that gives you some matrix bounds, but we can jump right into the more interesting part, really, which is part 4, which is I have an n by d data matrix, so each row is a vector observation of length d. This is an n by d matrix. And to start with, we'll say that the mean 0, the mean doesn't really matter. I'm going to start by assuming the covariance matrix is identity. We saw last time that once we have a result for the identity, it's easy to turn it into a result for a general sigma. And sigma hat then is nothing other than this matrix, and what we're interested in is the operator norm distance between sigma hat and sigma. So let's just call this the B. Let's call this thing B. And remember, one way to write the norm is it's the sup of B times U, where U is a unit vector, and you take the sup of that over all unit vectors. So how are we going to control this thing? What I want to show you that this thing is small, that with high probability, it's going to be less than something of order, square root of d over n. Okay, with high probability. So how are we going to balance something like this? So the trick is this, if you think about it, we're looking at b times u. If I fixed one u, that would just be a single vector. This would be a much easier quantity to deal with. The problem is we're taking the sup over all u, but u varies over this sphere. So u lives on here, and so it's like we're computing b times u and then varying u over this whole thing. So you can think about it as what we're trying to balance some function over the sphere. And we're going to use a trick that we used before, both when we did minimax theory and when we did concentration measure, which is when we have an uncountable thing like that, often a good trick is to create a covering, a finite covering, because that's much easier to deal with. So what we're going to do is we're going to put a covering like this. And the covering number, we're going to take a covering. Each one of these spheres has radius for now, let's say A. We'll pick A later. And you may remember you bounded something like that in one of the homeworks. It turns out that the covering number, n of A, the number of balls to cover the sphere, is bounded by something of this form. Roughly speaking, it's like 1 over A to the D of that order. And I think to make things work out in the proof, if I remember, I have here, yeah, I'm going to take A to be a half. It's going to be a convenient choice. So for that case, we're going to get, what does that end up being, 5D? Yeah, 5 to the D. So we're going to cover this with 5 to the D points. Okay. Now, if I take any U in that sphere, I can, so think about taking, let me blow this up a bit here. I picked this approximating set. If I take any arbitrary u, I can always write it as the closest point plus the difference. So I can take any u in the set and write it as, let's say, v plus w, where v is in this finite set. I should say that this finite set I'm going to call in the notes script n. I can't make a script n so good on the blackboard. That's just to look like a script n. So I can always write any u as the closest guy in the net. So this will be in this script n. And then this is going to be what's left over, which by definition is going to be less than a. We picked them to be a apart. And so the norm of a matrix B, that is the sup over u in the sphere, B of u, I'll just do the triangle inequality and say that's less than the sup of B of u u in the sphere, sorry, not the sphere, in the net, plus the sup of b of w, where w are all things of norm less than a half. But if you think about it, the sup of all things, I guess I should have made this the sup of all things less than or equal to 1. Not equal to 0, though. Actually, that's not correct. Let me put back equals. But leave it at equals, right? I just realized that there's maybe a small bug in the proof. Let's see. Because I'm claiming, yeah, okay. So now the claim is that, right, no, this is good. Everything's good so far. So now the sup of all things where w is less than a half, I can just rescale by a half and say that's less than or equal to the sup of all things less than or equal to 1, and the sup occurs when it's equal to 1. So this is equal to a half of the original norm. In other words, if I rescale the ball by a half, that's just going to be 1/2 the norm of the original norm. This is just the norm. Okay, so in other words, this is less than or equal to, and I can even write this sup now, it's a maximum, right, over a finite net, plus a half times the original norm. If I bring this half to this side, I get 1/2 of the norm of b is less than or equal to the maximum over the finite set. Or in other words, the norm of b, which was a sup over a continuous object, is less than or equal to 2 times the maximum over a finite net.
Could you explain again this part?
Yeah. What did I do here? The sup of this is certainly less than or equal to sup when this is equal to a half. I can only make it bigger. And then if I just take u and multiply and divide by a half, that's the same as putting a half out front and making this have unit norm again. In other words, the sup is defined arbitrarily the norm is defined arbitrarily to be the maximum for all vectors that have length 1. You can pick any length, but then it just scales the norm accordingly.
Here the SD is the d-dimensional ball or sphere.
Sphere.
But for sphere, the covering.
Well, I can make this less than or equal to, right, if I want, but I'm taking the sup, so it's going to occur when u is equal to 1 anyway. Doesn't matter.
But the covering number for sphere it should be of order d-1.
Yeah, that's okay. I made it d. You're probably right. This could probably be replaced by d-1, but it
It
won't.
seems like a bound for the ball.
Yeah, it's okay. It's it's of the right order, so it doesn't matter. It may be that I could put a d-1. Yeah.
Why choose a equals to 1/2? Can you just make a evaluation of
Why did I take a equals a half?
Yeah.
It's just going to be convenient. I mean, we're going to see that we're going to have to pick a certain choice eventually, and I just later on realized a equals a half is a convenient choice. Yeah, you didn't have to pick a half. What happens here is, you would have had something different than a half out here, then I would have had b less than some other constant here. This would have been a constant difference. It didn't matter.
Sorry. The sup norm of w is less than a half is greater than the sup norm of w is equal to half.
Oh, that's true. I think, though, isn't it the case we can show the sup occurs at the, I think we can show, so that's a good question. It's a bigger set. I think the sup occurs at the boundary.
Yeah,
So-
essentially because of the convexity.
Yeah,
You're
so
using
so
it.
I can replace the sup less than, and it's the same as the sup at the boundary, right? Okay, so to summarize, our original norm is now 2 times this thing, but this thing now is just b times u over, and now I have to control a finite number of things. Now there's a lot of them. There's 5 to the d or whatever it is. But each one of these is pretty easy to control. So let's do that. Now it's going to look a lot like the proof we did for Johnson-Lindenstrauss. It's going to be really almost the same proof, is that, we've got this sigma hat. Let's go back to what we're interested in. The norm of sigma hat minus sigma, which is actually 1 over n A transpose A. Remember, the true sigma here is I. That's the soup. By definition, this is an operator norm. It's a soup over the sphere, but we just saw we can make that 2 times the max over this finite net. And now I'm just going to break this like we did when we did the Johnson-Lindenstrauss kind of thing. Is I can rewrite this as 1 over n A transpose A minus I. Let's say take the inner product of that. Let's take that times U inner product U. For U in that, only in this finite set. Or in other words, this is 2 times the maximum for U in the set. I'm just going to rewrite this as and now we're going to do exactly the same thing we did in Johnson-Lindenstrauss. Each one of these, that's a row of AI times U. That's just a sum. Every element in there is just a sum. So AU squared, just multiply each of those and take the norm. You just square those things and sum them. So in other words, this is just the inner product of the ith data point with U squared, or in other words, let's just call this Zi squared. Now, what I didn't tell you is I've snuck in an assumption. This is a common assumption we've made a lot when we prove things, which is we're going to assume the Zi's are sub-Gaussian. You're going to get different rates if it's not sub-Gaussian. So then we can simply use a Chernoff argument. The probability that this is bigger than epsilon over 2, the probability over n times this, let's say epsilon over 2, or rewriting it in terms of the z's, and now I'm just going to do the same thing we usually do. You can do this on 2 sides and then do it on the right side, left side, multiply the answer by 2. And to do any of these, what do? I take e to the t of this is bigger than e to the t of this. I'm not going to go through it because it's the usual thing. And it's less than or equal to e to the t epsilon over 2 times the moment generating function, which is exponential by assumption. That's the sub-Gaussian assumption. So you end up with, I'll just put some constants in here. E to the c v plus t squared. And then the key is that now the probability that the maximum of all that is bigger than epsilon over 2 is simply less than or equal to 5d times this. I'm just doing the union bound. But this is slower than this. So this can be rewritten as up to some constants e to some, let's say, some other constant c prime times t squared. Remember, d is fixed here. I'm not letting d increase. So it's just a constant. And from that, we get that this is concentrating. If I set epsilon if I set this to be some small probability and solve for epsilon, you get that. I'm sorry, I'm doing this kind of sketchy. I realize I'm going quickly. But what you end up with is it's so similar to all the other Chernoff arguments we've done that I didn't put all the steps in. It's really just, again, that each individual one we can do Chernoff, and then you just have to multiply by the number of them by the union bound, which is 5 to the d. Set this equal to a small probability, and we conclude that sigma hat minus sigma is less than or equal to, and this is for, this t is, I should say, this is all happening with high probability. What probability? With probability, no, the probability this fails is less than or equal to, say, e to the minus c t squared. So when you set the probability to whatever you like, you get this t here. The key thing is this. This is going to be typically the dominant term. And then using the trick we talked about on Tuesday, we can get exactly the same bound for an arbitrary sigma.
There is a problem here. Here is a norm of b times u, but here on the first line, that's why first line, that is not the norm of the matrix times u. Here, less equal to 2 max.
This one?
Yes. This one is not, that is not the norm of that matrix times u.
No. I think it is. It should be u. Yes, you get.
That's right.
That's good. You get u transpose this u minus, and then u transpose u is the identity. Let's get back this.
The norm.
This is the matrix norm, which remember is the maximum of the vector norm.
But you use this inequality here. The right side is a vector norm.
Right.
How do you define the vector norm of b times u?
Just the usual norm. So
If your norm is u transpose b times u, it's 2b.
That's a good point. Well, let's see here. I'm pretty sure this is right. I think I might have. I see what you're saying. What he's saying, that's a good point. If I lost a term, I'm pretty sure this is right though. That his point is this, right? If I write down what this is u transpose b u, right? So there's a b transpose b. And so why don't I have an extra a? I think this is right, and I see your point. This is sigma transpose sigma, no, so this is sigma transpose u. It should be matrix norm of this times u is this times u is u transpose.
Well, we're using the units here, so I can't really increase it, right? I mean, one argument would be that the square can't be any worse.
No, but I think I've actually dropped something. This is, I'm positive this is correct. I'm just not seeing why right now. I don't think there's another bound missing. I see your point. It looks like there should be another, it almost looks like there should be the way I wrote it, another A transpose A in there, right? So I think I've just done something wrong in one step. Let me come back, I'll correct the notes and fix it up because I'm not going to spot it right now. I'm positive the result is correct.
I think if you expand u with the eigenbasis, then you're fine because you're taking the maximum anyway.
Oh, I see. You're saying if it
So
did
this term is basically the Raleigh coefficient.
the Raleigh quotient, that's correct.
And use a vector.
Yes, it just doesn't line up though with exactly what I wrote there, right?
But there you're also taking back.
I mean, what you're saying is, if I maximize this and choose U correctly, in other words, this is certainly true, but when I take the max, I should get this, you're arguing. Because when I maximize it, the maximizer will be like B over B times, say, some V over the norm of that. Yeah. So the maximum does occur at such a point that it's equal to U transpose BU, because this is precisely, right, this is the Rayleigh quotient expression for the largest eigenvalue of the matrix. So I may have confused you, because I confused myself, so I probably confused you too. I'll fix the notes and it'll be clear. I'm not gonna do it right now, but I'll fix the notes, it'll be clear, but the result is correct. I just left off some steps though. Yeah.
How much does this depend on the when we start off with the features where you
It doesn't depend on that. So,
the identity matrix that we had in there?
right. In fact, let's get back to it. So let me just say what the bottom line is in all this first, and let me answer your question. So first of all, there's a step missing in the proof, which I will add to the notes. Okay, so don't worry about that now. The important thing is how far is sigma hat from sigma. So far we are doing just the identity case. The answer is, for this analysis, it's d over n. Without extra assumptions, I don't think you can improve that. But there are other assumptions you can put on to get faster rates. But as long as we're in the regime where d is less than n, this is, where d is increasing but slower than n, then this is going to go to 0. And this is telling us that this is close to this in the operator norm. Remember why we cared about that? Because if two matrices are close in the operator norm, then Thales' theorem says their eigenvalues are close. And if as long as the eigenvalues aren't tied, that also means the eigenvectors are close. This is the reason why people are interested in this. There was a calculation at the bottom of page 2, just to remind you, that related the arbitrary case. So this is getting to your question. This is less than or equal to where this is the sphered data. These are the data that have been rotated to have identity covariance, times the operator norm of the original matrix. So now this is going to be of order d over n, root d over n. And now we have this extra term, and of course we have to assume the operator norm is finite, or none of this makes sense. So that just puts another constant in front. So we get the same answer for the general case. All right, let me make sure. Apart from that, the one missing step in the proof, I hope I got the message across. So this is, this is the basic starting point for analyzing random matrices. There's a lot more, of course, you can do with random matrices. I focused on this one example, which is the covariance matrix, which is, one of the first things people are interested in. But this type of analysis is used for lots and lots of other problems now in machine learning and statistics, where you need to control something about a matrix, typically like its operator norm, and you need some sort of concentration inequality. Okay, let's see, was there anything else? I felt like there was one more question that I said I was going to answer. The general sigma maybe that's it. The sub-Gaussianity, though, I did this step very quickly, but of course, when we do this turnoff inequality, we had a moment-varying function. Without the sub-Gaussianity, we wouldn't get it. We wouldn't get this result. Okay, so what my plan is now, I'm sorry about the confusion there, is I thought I'd use the rest of the time, rather than, there's a couple more topics here that I just included for your interest. I think I'd rather do differential privacy, though, given that we're in the interest of time. If you want to see, I put in something about what's called restricted isometries and compressed sensing. So if you're interested in that stuff, it's just another application of the random matrix theory in a different scenario, and there's another example at the end as well. They're all doing the same tricks. The most important trick in all of this was recognizing that you're taking a supremum over a sphere, and that all you need to do is cover it with finitely many points, and then do Chernov's inequality. So that's a little flavor. This one plus the Johnson-Lindenstrauss is very similar. A little flavor of that kind of analysis. There's also, I wanted to mention, remember some of our critical inequalities were what? Hoeffding's inequality and Bernstein's inequality. And you might wonder, are there similar inequalities for matrices, for random matrices? And there are. So I didn't include those, but if you're interested in that, there's a very, very nice review paper by Joel Trope. Something like user-friendly bounds for matrices, random. I can't remember the exact title, but he shows you what the matrix version of Hoeffding's inequality and Bernstein's inequality are. Okay, just in case you're interested in that. Okay, good. So I did manage to keep some time now to just introduce a little bit about differential privacy. So what is differential privacy? For those of you, most of you haven't seen this before. It's a way of releasing data while protecting people's privacy, as the name implies. This is a very, very old problem, and differential privacy is a relatively recent proposal for how to do this. And I have to say, it's a little bit controversial because in the theoretical computer science community, it is now considered the method for protecting privacy. I would say in the statistics world, nobody uses it. And I actually went to a very interesting conference once at the Institute for Applied Mathematics at UCLA. There was a really interesting conference where half the people were from computer science and half the people were from statistics. And the idea was to try to bring everybody together because, after all, statisticians are extremely interested in this privacy issue. I have a couple of colleagues, for example, who have been consulting for the US Census Bureau for many, many years, and this is something they've dealt with their whole careers, is how do we release information to the public without compromising everybody's privacy? And you may remember a few years ago, did anybody remember the Netflix challenge and the disaster that happened? Did you hear about that? That Netflix released a bunch of their data and said, if anybody can improve on a recommender system, we'll give them $1 million. And some guys eventually won this $1 million prize. But they were careful to strip everybody's name and identifying information from the data set because they didn't want to compromise people's privacy. But instantly, a couple of very smart cryptographers did some very clever things using other information they found around the web, and immediately, well, not immediately, but very quickly broke the privacy and figured out who everybody was on this data set. And Netflix, I don't know if they may have even had lawsuits. I'm not sure what ended up happening, but you can see why this is a big problem nowadays. We have these huge data sets, and you can get in big legal trouble if you release information. On the other hand, if you can't release information, what's the point of collecting data? So we have this kind of dilemma. And the nice thing about differential privacy, what I like about it is it's a very precise and simple definition of privacy, and it's been well studied now. There's a whole industry of people writing papers about it. On the other hand, it's a very, very strict protocol. It's very hard to achieve this thing called differential privacy. And the reason why statisticians don't use it is because in my experience, if you try to actually use it in real applied data sets, not toy things that you're writing for a paper, you end up having to add so much noise in the data that there's no information left. So what's missing, I think, is something in between. Is there something less strict than differential privacy that still preserves information? So let me explain to you how it works. The idea is very, very cool and very simple. And keep in mind that apart from this technique, the broader issue of how do I preserve privacy is a very, very pressing issue. This is especially true, by the way, in healthcare, right? Where people analyze healthcare data, and nobody wants to have their own health records exposed somehow. And what makes it difficult is you don't know what information an adversary might have access to, what side information. So abstractly, the problem is just this. I have a database, which is just, we'll just think of it as n vectors. Okay? Each xi is in some sample space, we'll just call it script x. All right, so key fact for differential privacy that we'll come back to. The sample space is known. What do I mean by that? Well, when you get a data set, you look at the range of the data where, if you plot the data, you don't know really in general where could I have gotten data further away and, what's the support of the distribution. It's actually an unknown quantity. But throughout differential privacy, we're going to have to treat it as if it's completely known. We know the data lie in the unit cube or something like that. And so here's the problem. I don't want to release x. I want to release some other information, let's call it z. So I want to take x, do something to it, and release z. And I have two competing goals. I want z to not release much information about any individual, but I do want it to have some useful information. So there are two conflicting goals there. I mean, I could just throw x away and generate random z's. I've definitely guaranteed the privacy of everybody in the database, but you haven't released any useful information. So somehow we're trying to balance these two things. So one of the main definitions in the field of differential privacy is the notion of a neighboring database. Suppose I have two databases, that is, two collections of vectors. They're the same everywhere, except I've taken one data point and just popped in a different data point. This is xi, this is xi prime. The rest of the data is the same. In that case, we're going to say that xi and xi prime, I'm going to write them as twiddle. It just means they're neighboring, those are called neighboring databases. Okay. And then here's the definition of differential privacy. We're going to say, we're going to do the following thing. This is what's going to happen. I'm going to input my data x and output something. We haven't said what it is yet. And I'm going to do it using a distribution, q of z given x. So just think of it as a conditional distribution. You give me x, and I output z with some probability distribution q. We haven't decided what the q is yet. So unlike typical data analysis where nature is generating data from some distribution, in this case we're picking the distribution, which is nice. But we have to pick q to satisfy this notion of differential privacy, and this is the definition. That the soup over all pairs of points, x and x prime, that are in the sample space, and actually in the sample space to the nth power, and such that, so for any, in other words, for any pair of neighboring databases, when I look at this distribution, and I better look also the soup over all sets B, the probability that my output falls in B, given x, and the probability that it falls in B, given x prime, is less than or equal to e to the epsilon. Epsilon is a small number close to 0 that you're picking. That's the privacy parameter. This controls how much privacy you're getting. So let's look at what this is saying. This is saying pick any set B. The probability that z falls into B, so any probability statement you make about z, if I switch one person in the database, then the probability, this ratio probability, changes by e to the epsilon. Again, if you think of epsilon as small, this is close to 1. Which means if it's close to 1, changing one data point, it's saying, isn't having much effect on the output thing.
But it's less than equal to, right?
Less than or equal to. Well, you can, from this, because of the symmetry, it implies also that it's bigger than or equal to e to the minus epsilon. Because you can just switch the role of x and x prime, x and x prime. So it's between e to the epsilon, e to the minus epsilon. If you think of epsilon as small, just think of this as 1 plus epsilon, so it's bounded between 1 plus epsilon and 1 minus epsilon, basically. Now, So this is a constraint. This is a constraint on the queue. This is no guarantee, again, that the queue preserves information yet. This is just a privacy guarantee. So let me first of all give you some intuition. Why does this actually guarantee privacy? There's many different ways of seeing this. I mean, they have proofs that certain types of cryptography attacks can be thwarted if this is satisfied. But let's think about it a little bit more statistically. Suppose you have your friend Joe, and you want to know, is he the ith guy in the database? Right? So I want to test the null hypothesis that some xi is equal to s. S is just Joe's, let's say these are like a bunch of pieces of information about each individual, and I look at my friend Joe, I look up his address, his age, his medical history, and that's what S is. And I want to, say, do a hypothesis test that it's Joe versus some other guy, say T. So the point is that this is about an individual I. Can I do a test like that? And it's not hard to show that if your release mechanism satisfies this, that any alpha level test for this, any level alpha test, has power at most alpha times e to the epsilon, which for small epsilon is like alpha. In other words, the power is pretty close to the type 1 error, which means it's a useless test, right? Because you can always just flip a coin with probability landing heads of probability that has alpha is like a type. That's an alpha level test that has power alpha. Power, for a test to be useful, it has to have power error 1. And the worst case is that the power is the same as the type 1 error. So what that's saying is any hypothesis test you try to construct is going to be a useless test, very low power. And that's true no matter what other extra information the person might have. This didn't refer to whether the person has other outside information. In fact, they may know the entire database except for person I, and this is still true. So it's saying it's hard to detect anything about an individual person. If you want to, I didn't put the proof here, but there's a paper by myself and Xuneng Zhao. I forget what year we wrote that. Which has the proof. It's a very short proof. I think it was 2010. But there's another way to see that this is protecting privacy, which is, let's pretend you're a Bayesian. This is actually a time when it's useful to think from a Bayesian perspective, because you might have lots of prior information. If you're really worried about an attacker exposing information about the database, your concern is not just the access to Z, but that they might have prior information. They might have other information. And so the question is, suppose somebody has prior information. Maybe they already know a lot about what's going on. The question is, does releasing this new data, Z, change their prior? Does it? I mean, if their prior already has a lot of information, there's nothing you can do about it. The question is your database inflating their posterior probability somehow? And the answer is no. So let's think about it in terms of prior odds. Let's look at the probability that xi is your friend Joe versus it's some other guy, T. These are now subjective probabilities. This is your odds that person I is S versus T. Okay, this is somehow you can use whatever external information you have, you come up with the prior odds. And now I want to look at the posterior odds and say, have I changed it? So for example, you might have, say, maybe it's 50-50 or whatever, but maybe when I see Z, it changes the odds quite a bit, in which case I've somehow by releasing Z, I've given you more information. But it's easy to see if we just do Bayes' theorem, the probability that xi is S, given that you've seen Z now, versus this, we just do Bayes' theorem. That's the probability of Z given xi is S times the prior probability xi is S. Xi is T, given the probability xi is T. I just did Bayes' theorem. But this ratio is precisely the probability of Z after changing one record. So that's less than or equal to e to the epsilon times the prior odds. In other words, your posterior odds, that it's Joe versus Jim, whatever, after seeing z, the posterior, this is again close to 1, so you haven't changed your prior very much. Okay, so that's kind of the intuition about why people like this guarantee, that somehow it's not providing too much information about individuals, a particular xi in the database. Yeah?
Why for every pair, not just like for the database that I have? It's like some databases happen to be more private than others, something like that.
That's a good question. Why for every pair? Because, so this gets to some of the controversy. Because, so I should say the people who invented this was Cynthia Dwork and her colleagues, they came from cryptography, okay? They're assuming the worst possible thing, that there are smart people out there who are trying to attack you, have lots of other information. They want the strongest possible protection they can get. So you could argue that this is too strong in many different ways. Like, for example, maybe doing it over the entire sample space is stronger than you need. I'll show you an example, in fact, where that makes it very large. But they want the guarantee to be really, really strong. And to get the guarantees they want, which is that certain cryptographic attacks can't work and so on, they really need it to be over the whole sample space.
So for these hypotheses, what sort of prior probabilities mean? Because xi itself is unknown.
Yeah, but I'm going to, right, this would be for anyone. For some reason, just imagine for some reason, like I'm the guy's cracking the Netflix thing, and I'm looking at record 5 and I think, I think this might be my friend Joe. Can I test that hypothesis?
Shouldn't that be in zi?
No,
Zi is
I'm trying to, no, you see Z.
Oh.
I'm trying to say, can I go back and infer the original database?
So in a way, you want to release as much information as possible without being identified.
Right, you don't want to be able, you want to release some information where it's not useful, but you don't want people to make inferences about individuals. That's the goal.
I guess this is a big question. Can this somehow be analyzed from an information theoretic?
Yeah, there is a lot of connections actually with information theory. There's some recent papers, in fact, about that.
Before I actually come to CMU, I read a paper by a non-computer scientist. His name is Alessandro. So Alessandro actually successfully predicted 80% of all the SSNs of the entire US from a non-computer science point of view. So I wonder whether this will really be usable in the real world.
Well, that's an excellent question. So let's go through now how you do this, because I haven't even told you how to do this yet. And then let's ask, is this practical or not? Okay, because I think that's a really important question. First of all, how do I actually implement this? So there's a variety of ways of doing this. It's a very active area. But one of the simplest ways, and probably I think the first one that they came up with, is called the Laplace mechanism. So this is one of the rare cases in statistics where the normal doesn't play a special role. It's the Laplace distribution. Let me explain. So suppose I've got a function that takes the data into the real numbers. So for example, just to have a concrete example, let's suppose all I want to really know is what's the mean. Somebody just asks me, what's the mean of your database? I could just hand them the mean, but that's not going to satisfy this definition. So is there something I can do to make it satisfy the definition? So what we do is, and this gets to your question about the sample space, we define something called the sensitivity, which is the maximum, again, over all pairs in the sample space. I compute this function of interest, it might be the mean, on any two databases that differ by one person, and I ask what's the maximum difference that can have over any neighboring database. So I have to be able to compute this number. This is just a number. And now here's the release scheme. You ready? This is how you do it. The z I'm going to release is I compute the function of interest on the original database, say x bar, and now I add a bit of noise. I add noise sigma w. What's sigma and what's w? sigma is the sensitivity over epsilon. So sigma is going to be big if either the sensitivity is big, this is really measuring sort of how stable this function is. If I wiggle it around, how much does it change? And epsilon is the privacy parameter. Remember, smaller epsilon is more privacy. So as I make epsilon smaller, sigma gets bigger. I have to add more noise. And what's W? W is a draw from a Laplace distribution. And we've never talked about the Laplace distribution. So in case you don't know what it is, it's just a density that looks like this. It's 1/2 e to the minus W. And you might wonder why Laplace, and I'm going to show you why in a minute. We're going to prove that this satisfies differential privacy. It's very simple. And you can see that Laplace, why it plays a special role. This means 0. It also needs variance. Was it 2? Right, yeah, variance is 2. It looks just like a Gaussian, except the tails die off a bit slower, and it's got this kind of peaked behavior at the origin. So I claim if I do this, that we're going to satisfy differential privacy. Let's prove it, because the proof's very simple. Put that there.
So here you change the d-dimensional x to a one-dimensional.
So far, we're only releasing a one-dimensional statistic, correct? So far.
We're kind of assuming this is a one-time event, right?
That's another question. What happens if I have to do this many times? Hang on, these are all great questions. So we're working up to it. That's hinting at why statisticians don't necessarily find this so useful. All right. Well, let's just convince ourselves this actually satisfies differential privacy. So look, this is just, if I just do a change of variables and get what's the density of z, it comes from W. So it's the density of z given x is epsilon over 2s e. This is just doing a location scale transformation. Right, it's just the Laplace distribution shifted by f of x and scaled by this sigma. Okay, so that's the density for z given x. And to see that this satisfies differential privacy, I expressed it in terms of probabilities of events, but we know if we show the density satisfies that ratio, then when I integrate it, it'll also satisfy that inequality. So I'm just going to check that p of z over x and p of z over x prime satisfies the required quantity. Well, the constants drop out, and we just have e to this thing and e to this thing with the f prime. So I get e to the epsilon over s, z minus z minus f of x. Right, I just took the ratio. Now I'm going to add and subtract f of x here and say it's less than or equal to, do the triangle inequality, f of x plus f of x minus f of x prime. This cancels with this. So I'm left with e to the epsilon s. But what is f of x minus f of x prime? That's at most the sensitivity. That cancels, and we get e to the epsilon. You can see why they chose the Laplace distribution. If you'd stuck in a different distribution, this wouldn't have happened. If you try it with a Gaussian, it's not going to all cancel out like that. So it's the distribution which makes this. It allows you to to bound ratios basically for the Laplace distribution. So let's do it for x bar and see exactly what happens. Suppose my f of x1 is x bar. Now, what's the sample space? Let's suppose that each xi is in an interval minus a to a. And we have to know what a is. what is the sensitivity? How much can I change x bar if I change one observation? Two a over n. So there we go. Here's how you do differential privacy for the mean. You take the mean and you add that divided by epsilon, so 2a n over epsilon times w. Very simple. All I do is take my mean, add a little bit of noise. I now guaranteed that I satisfy differential privacy. Now, let's ask the question, have I obscured the information very much? How much information is in my answer? Well, it depends, right? Because this is just an order one random variable. That doesn't look so bad. The good news is that this is n. That's really good news, right? Because we know how far is x bar from its population, what it's trying to estimate the population, 1 over root n. So this is much smaller than that. Of course, the devil could be in the constants. This epsilon might be 0.01 or something like that. That could be pretty big. And also, this a, how wide is the interval? First of all, you have to know it. You have to know for sure the data following this interval, and a could be big. So whether or not this is big or small depends on the problem. It's very context dependent. If you're doing salaries and of people, and Bill Gates might be in your data set, a could be huge. On the other hand, you might say, I'm just not going to allow people in the database who are like way, outliers, who are way out there. And then maybe you can make a small again. So there's all kinds of practical questions that you have to deal with like that.
I'm having a hard time seeing how, if we just released X bar itself, why that would not satisfy.
Why doesn't just relieving X bar satisfy differential privacy?
It's just one.
Yes, but don't forget, if I take the soup, if I look at the distribution of X bar, given X, the distribution X bar prime given X prime, and I look at the worst case over all possible neighboring things, I can make that huge. I can make something have 0 probability and positive probability somewhere. You really do need to add noise. These would be delta functions, so this really requires that you're, in a sense, you're smoothing things out by adding the noise. And you can see why there's, quickly an industry form, because you can take everything you've ever thought of, classification, empirical risk minimization, principal component analysis, logistic regression, and say, can I make a differentially private version of it? And then once you make it, you say, how much noise am I adding, or how much information am I losing? If you want to put more information theoretic, they can say, can I come up with one that's better, and so on. So that's why there's a lot of interesting papers about this. But let's keep going, because let's get to the issue somebody over here raised, which is, so when this field first started, this is how it was cast, is that there's a curator who owns the data, and you send a query. I would like to know the mean of the database, and the curator sends you back this differentially private answer. So there's a few problems with that. One is, what if I have more questions? Now I want to come back with another question. You have to guarantee you have differential privacy over many queries, but also nobody analyzes data like that. This is the biggest problem with this area. Is that I'm going to show you in a minute you can actually release an entire data set differentially privately. This is the right way to do it. Because you will not find a statistician in the world who will analyze a data set if you don't actually give them the data, right? If you just have to send queries, or forget it, they're not going to do it. So that's a sociological difference between the theoretical CS world and the statistics world. But let's first of all, suppose you were given D queries. Well, suppose, for example, I now had a function f that took R to the D, took the sample space, x to the n, down to R to the D. So instead of providing one real number, you're providing D numbers. So for example, suppose it was a vector valued data set, and I'm providing x bar 1 up to x bar d, just as an example. somehow you're estimating D quantities now. At least that's a little bit more general. All you do, the same proof goes through, it's just that you define the sensitivity in terms of the L1 norm now. This is a vector, and this is a vector, you take the L1 norm. And that becomes the sensitivity. And it's not hard to see that the same analysis goes through, you just have to add noise proportional to this sensitivity. So I won't repeat the proof, it's exactly the same proof. But let's actually see what happens over here. So this is my X bar. I now have a D-dimensional problem. So what do? No problem. I take X bar. I add some noise. But the sensitivity, we're taking the L1 norm. We're summing up the coordinates. And if there's D coordinates, the sensitivity gets increased by a factor of D. Roughly speaking, for D to release D pieces of information now, the sensitivity's gone up by a factor of D. And you have to increase the amount of noise you're adding by D. So you can see the bad things are starting to happen, right? That's a lot of noise all of a sudden. So there's a problem, at least with this mechanism. There will be a problem with just blindly trying to add Laplace noise whenever you want to release information, because if it's D-dimensional, this is going to be a huge amount of noise. And that's the amount of noise you're adding in each coordinate. So every single piece of information you release is now extremely noisy. Okay. Well, what we'd really like to do, so the reason why I myself, it's not an area I've worked in very much, different from where I was at, but I do have a couple of papers in it. And the reason why I wrote the paper with Shonju was we wanted to say, well, let's try to make this more palatable to statisticians. Statisticians were reacting very negatively to this. They want data. So we wrote a paper about how do you actually release data. You know, I want to give out a data set, not answers to queries. So there's a variety of ways you can do that. So somehow I want my Z to be something like a sample, let's even say a sample of size n, that somehow has some of the information in the original data set, but still preserving differential privacy. And there's a few ways to do it. Here's one way to do it. We take our original data set. Again, I'm going to have to assume we're on a known domain. Let's say it's a cube, just for simplicity. What I'm going to do is estimate the density. And let's start with the simplest estimator, the histogram estimator. So all I'm going to do is divide things up into bins. There'll be m bins. And I'm going to get the counts. So this will be like C1, C2, you know, the usual thing, right? I'm going to just get the counts. And now the trick is this. I'm going to differentially privatize the histogram. Okay? And so what I'm going to do is take each count. I'm going to add, and it turns out the amount, this is the right thing to do, is you add a Laplace random variable. Sensitivity turns out to be bounded by this. So that's going to be my new privatized count. The only trick is if this could go negative. I could take a count, W could be negative, this could go negative. I'm going to make it minimum of that 0. Okay, and this defines a new set of counts and gives me a density estimator, Q hat. And it's easy to show. There's a nice property that once you have something that's differentially private, anything you do after that is still differentially private. It's trivial to show that. So in particular, if I draw Z1 to Zn from Q hat, this is now a data set, and it's differentially private. The whole data set is differentially private. Okay, now, how do we answer the following question now? Does this contain much information? So one way to answer that, I'll tell you how we did it, was to take a kind of statistical perspective and say, well, if I think about, I'm drawing observations from this density estimator, let's just ask, is that a very good density estimator? It's not the standard density estimator because we've perturbed all of the cells. but there's some good news here. So let's say that we view this now as an estimate of the underlying but unknown true density P. And let's suppose we know to do density estimation, we're going to have to make some assumptions. So I'm going to assume it's Lipschitz. So first of all, does anybody remember what would the minimax rate be? Suppose I want to look at the L2 distance, let's say, the sup over P's in the Lipschitz class, N over all density estimates. You remember what the minimax rate is? I did, because I had to look it up, to be honest. It's N minus 2 over 2 plus D. So, and to do that, by the way, you need to use M to be like N over D, 2 plus D Ns. Okay, so now I can ask, one way to assess how much information is in what I've released is, let's just say, what's the rate of convergence of this thing? And the good news is it converges at the minimax rate. So the expected value of Q hat minus Q in squared error is the same. So at least that's some evidence that this way of privatizing things, we haven't lost too much information. At least in some sense. At least the rate is going down at the right rate. The constants could be quite a bit different. But at least in terms of rates, we've preserved a lot of information. Yeah.
I wonder whether a hacker would actually do some kind of like group lasso or kind of like a clustering to recover the cells, because each cell is still having the same kind of transformation together, right?
But we have the different, but it's differentially private. So we know that they can't do that, at least up to the guarantee given by differential privacy. But you could imagine them having priors about what those cells look like, and then using the released information to compute the posterior, but we know it can't change by more than e to the epsilon. It's guaranteed. So that's the nice thing about differential privacy, is it gives you this very concrete guarantee.
How did you pick the value of M?
Well, I did a lot of playing around with it until I got the right answer. I just, I knew what to do. Yeah. No, but you know how to do it too, right? If I said to you, in the final exam next week, just kidding. If I said find the minimax, rate for you, or the risk for using this, you know how we do those calculations. You would know what to do.
Life Q.
Oh, that's a mistake, is what Q is. That's supposed to be the original density P. So here's kind of also, I thought, a kind of cute use of minimax theory to at least give some insight about differential privacy. But I want to say that, what's funny? I forgot to put this is going to be a really funny video.
I heard you.
Okay, all right. See, it's because of my concerns about privacy that I didn't use the microphone. Sorry about that. All right. So this is in some sense good news, but there are still problems. I don't want to give you the impression that this is guaranteed to work well. So let me give you a type of an example where even though technically it's converging at the minimax rate, it still might give you a distorted picture. So let me just draw kind of a cartoonish thing. And it's better if you imagine this in high dimensions. If we were trying to do like a high dimensional thing, you can imagine there could be big gaps in the data. But let's just do a one-dimensional version. Suppose my histogram, just to make it really clear, looked like this. I mean, this is very extreme, but there's a bin here, and then a big gap here. More realistically, just imagine that there's big gaps along there. And so the original data have a very uneven distribution. Well, differential privacy doesn't like zeros. Zeros are very revealing. Because you're taking ratios of probabilities. If I had a 0 probability of putting something there, I take a ratio, I'm going to get infinity. So, in other words, when I add, don't forget I have to add noise to every bin. These are going to end up with positive things once I've privatized it. And this is going to come down quite a bit. So we're going to get a histogram that we're drawing from, which is sort of qualitatively quite different from the original histogram. It might formally still have this minimax property, but it can look very, very different in practice. I guess that would show up, in the constants and things like that. In fact, anytime you have data, and imagine a high-dimensional data set where you might have clumps of data here and there, and data, I don't even know where the edges might be. Maybe the data are here, and then if there's areas where there's zero probability, when you differentially prioritize it, you're going to fill in. There's always going to be sort of positive mass everywhere. You can't have regions of zero mass. That's what protects people. If there was like a big zone with nothing around it and one guy sitting there, he's ripe for being attacked by a cryptographer. So you better make sure that your privatized data have lots of stuff around them. And so that's what adding this noise does, is it kind of smooths everything out. So in practice, in principle, this seems to work pretty well if you do things this way. But in practice, you could end up with examples where the privatized data look very different from the original data. So I just wanted to throw a note of caution there. Yeah.
I guess this kind of brings back to the fact that some databases are inherently more private than others in some sense. And another thing is kind of I would expect some queries would be able to get more information out of the database than others. Do people use this to come with?
Yeah, that's right. So this is all kind of very blunt, what I'm doing here, right? We're just saying we want to have a certain guarantee and that's it. You might want to protect different parts of the database more than other parts of the database. You might want to release queries with more information and sort of spend your privacy in different ways. So there are a lot of papers about different flavors of differential privacy and different ways of dealing with things. This is really just kind of the basic idea. It's a very, very rich area, and I have to be honest, I haven't been able to keep up with it because the papers come out faster than I can read them. There's a lot of people working on this now for obvious reasons. It's a very important area.
In practice, a lot of real data is discrete, not discrete. So, but I get the sense that if you go back there, you perform worse if your set is bigger, and in some sense, discrete sets are much smaller.
No, they're bigger.
Okay.
So discrete data are a bit of a problem. Let's think of the simplest example of a discrete data set, which is a two-way contingency table. So just imagine I've measured two discrete variables. This is your income level, say I've divided it in 5 categories, and your age level is divided in 6 categories. And this is what happens in a lot of census data that's released, is that you release the counts. So it's discrete. The problem is, usually when you release data of this form, it's not just 2 variables, it might be 30 variables. And when you think of a 5 by 5 by 5 by 5 by 5 by 5 contingency table, most of the table are going to be zeros. But you can't have zeros in differential privacy. When you privatize it, you're going to put something in all of the cells. And so this is one of the complaints. When I went to that conference, some of the yelling back and forth was some of the very applied statisticians saying that this is the kind of data they're dealing with every day. And if they tried to do this differential privacy, they're releasing junk. I mean, there's just no information in what they're releasing. And so there seems to be kind of a gap there. And at least, I should say this is high dimensional. I mean, if only you only had a few categories, of course, it's okay. But if there's a lot of categories in your discrete data, it seems like the differentially private methods are not going to be able to release useful information, at least if you try to release the whole table. You could say, maybe I should only release parts of the table. Maybe I should just look at the marginals. Maybe I look at the one-dimensional marginals. Maybe some of the two-way marginals. If you restrict what you release, then maybe it's not so bad. So I think there has to be a lot of thinking about how much information should I release? Should I release everything? Should I release just certain aspects of the data? And you really have to try to balance the privacy with the amount of information that you're releasing.
So isn't that pretty much a fundamental problem with the curse of dimensionality, since isn't it? We want data to grow exponentially, but it doesn't. So in high dimensions, almost everything is going to be data is going to be.
That's right. So you're right. This is just the curse of dimensionality. That in high dimensions, the data are quite sparse. So you could argue that the data to start with are maybe problematic. Differential privacy is only making it worse. But suppose this is the census of the United States. sparse or not, this is the data, and it's the truth, right? In this case, there's a truth, which is this is how many people fell into this category. And so it is high dimensional, but there's a well-defined truth that you'd sort of like to preserve, which is definitely going to get messed up more when it's high dimensional. But it is, in some sense, you're right, there's another aspect of the curse dimensionality. The more complex the thing you're trying to release, the more noise you're going to have to add. And it's, by the way, let me just say something else. I've only talked about one mechanism, which is adding the class noise. There are other ways to create differential privacy, but they all amount to morally the same thing. They're like adding noise to the data set effectively.
So in this case with the high dimension, it seems like really what's really killing us is this the size of the support, right?
Yeah, the size of the
Shooting
support.
the dimensions independently. Could you get around that if you did a dimensionality reduction on your data first?
That's a very interesting idea. Why don't I reduce the dimension first and then release the data? That's fine, but your dimension reduction technique better be differentially private. Every step of the analysis has to be differentially private.
Oh, well, I mean, that defeats the whole point, right? I mean,
That's why it's not easy to do it. Yeah. I mean, this is why it's still an active area of research, right? Because of questions like this is, how to deal with all these things.
So if you reduce it, add like the noise and reconstruct it and release that.
Yeah, and there's a nice paper by Kamalika Chaudhuri from the University of San Diego, where she's got, I think she has a paper about differentially private principal component analysis for reducing the dimension. You'll see there's papers about differentially privately doing the lasso, things like that. You can take any technique you can think of, and somebody's probably written a paper about how to do it. And here's another interesting challenge. Obviously, I'm not going to get to the rest of this, but I'll just tell you that the other interesting challenge is what's the best you can do? How would you do a minimax analysis of this? How do I know there isn't something? Well, in this case that I just did, we matched the original minimax, right? So you're probably not going to improve on it very much. But in other instances, you might ask, what is the best way to somehow enforce differential privacy but maximize the amount of information? That's basically a minimax problem. And there's a few papers on this called Lower Bounds for Differential Privacy Under Different Circumstances, but it's not completely answered. There's a nice set of papers by John Ducci and Martin Wainwright and Mike Jordan, where they have some lower bounds for differential privacy. But what they found, if I remember correctly, always dangerous to go by my memory, but if I remember correctly, they weren't able to get lower bounds in general for differential privacy. They changed the definition a bit to something called local privacy, which is actually a stronger type of privacy, and they were able to get minimax lower bounds. That any differentially private scheme, you basically have to add such amount of noise. But I'm not sure that actually answers the original question, which is what's the best you can do just under plain differential privacy. It has been answered in certain circumstances, like I think for tables and things like that, there are lower bounds. So there's a lot of interesting questions. Okay, and this has led to another area. So recently there's been a whole slew of papers, like in the last year or 2 years. Very exciting area. Okay, so this is also so the person who invented this, as I said, was Cynthia Bork, Adam Smith, and I forget the other, not that Adam Smith. Although if you go to his webpage, he does write my 2 books, and he puts the original Adam Smith's On the Wealth of Nations, and he has a sense of humor about it. But I forget who the other co-authors were, but at any rate, now I forget what I was telling you. What was I telling you? Before I started telling jokes. So they have a whole set of papers saying they can use this for another purpose, which is called what they call adaptive data analysis. So it's what statistics we would call selection bias. In CS now they call it adaptive data analysis, which is you look at the data and you estimate a quantity. Then after looking at my estimate, I decide to go back to the data and estimate something else. Then I look at that estimator and then I decide to go back and do something else. We do this all the time, right? Forward stepwise regression. We estimate something, we choose another variable. We estimate something, and so on. So they discovered this now, and they call it adaptive data analysis. And their way of how do you prevent bias from leaking in? And this is something we all worry about. But what they basically do is they basically use differential privacy. They're not using it for privacy anymore. They're just using it to get rid of the bias and looking at the data. Because the idea is that if suppose an analyst keeps looking at the data and making decisions about the data, and every time they look at it, the computer forces it to be differentially private. What does that mean? It means they're not getting much information about the individual data points, so that should somehow reduce the amount of selection bias that's occurring by repeatedly looking at the data. And so you'll see recent papers, and by the way, I've tried to convince them, I'm trying my best to change the name to interactive data analysis. Because in statistics, adaptive means something else. Adaptive means trying to get minimax rates that adapt to the smoothness of the function class. So I'm just trying to convince them I should call it interactive data analysis. I don't think I'll succeed. But it's called adaptive data analysis, but it's using differential privacy, but it's not being used for privacy. It's just being used to deal with this problem of what if I repeatedly look at the data while I'm doing data analysis. And so differential privacy just happens to be one way, but not the only way of dealing with that. Privatizing the data means somehow I'm not looking too closely at the data when I'm making my decisions. Okay, so there's a few other ways of achieving differential privacy. I obviously don't have time to do it. And I'm sorry I didn't type up the notes. I was pretty good about it all year. It was just the last topic I just didn't have time to get to. But anyway, that gives you a flavor of what it's about. And this is just the tip of the iceberg. It's a really, really interesting area. There's a lot of stuff you can find out there. I believe that Cynthia and one of her colleagues are writing a book. So there'll be a book on this pretty soon. The first book on differential privacy, I think. But I'm not sure that it's out yet. But you can still find lots of literature on it anyway. Okay, any questions? Yeah.
Can I ask a question at the beginning of the class? Is there any differential privacy research done in field of text, especially like medical text,
Oh,
unstructured text?
is there differential privacy research being done in the area of text? I actually don't know. I'm not sure. That's a good question. You know, if there are CS people working in that area, then I'm going to say yes. Just going to guess yes, because they try to apply it wherever they can. But I don't know. I'm not familiar enough with that area to know. All right. So listen. Remember, next week, please everybody be on time. And 2 minutes goes fast, so make sure you practice your presentation. And we'll have lots of fun.